Excuse me. Thanks, Hernan. Mr. Hernan said my name's Ron Lowry. I'm the Eastern Area Manager for Hazard Control Technologies. So cover, for the most part, the Eastern United States and Eastern Canada. In addition, I've got 38 years in the fire service, and I'm currently a fire chief with a volunteer fire department in Allegheny County, Pennsylvania. So pretty intimate with F500 for its applications, both from a company point of view and from a fire department, fire operations point of view. So as Hernan said, the presentation tonight is on Class B fires and spill control. We're going to start out, I guess, from the beginning. So, we need to look at the history of firefighting agents, where we've been and where we're going to. So, in the history of firefighting, water's been it. For a long time, water was the fire suppressant agent for everything until hydrocarbons came along. And we've found with hydrocarbons that water really isn't a good solution for that type of fire, and in fact can make the situation much worse because that burning fuel can actually float on top of the water that we're trying to use to extinguish the fire. So then we came into the advent of foams. Like here, the initial foams were created around the 1800s by mixing, aluminum sulfate and sodium bicarbonate with water in a foam generator to make foam. From there, we went to protein-based animal fat foams. From there, we went to the surfactant, the film-forming foams, the AFFFs and the ARAFFFs. Then we had the issues with the chemicals that are used in those, and we've now progressed to the green foams that are, none of the fluorinated compounds. But in addition to that, we now have encapsulator agents and encapsulator technology. That technology is covered under NFPA 18A. It's actually an older edition here we have on the slide. The 2022 edition just came out in January with a lot of really good updates within the 2022 standard regarding both applications and application densities for some of the fixed systems applications, as well as test protocols for Class D metals and some other things around lithium-ion batteries in the annex. But encapsulator agents, as I said, are covered under 18A. In particular, Section 7.7, the spherical micelle stability test that you can run on your encapsulator to prove that it truly is an encapsulating agent, which F500 is, and it complies with that NFPA 18A Section 7.7 test protocol. So when we look at encapsulator agents, what are they? So kind of a textbook definition, it's a water additive, again, not a foam, it's that new technology. Water additives whose basic building block is a spherical micelle. Those micelles are capable of encapsulating carbons and hydrocarbons, both polar and nonpolar, in both liquid and, most importantly, in the vapor state. So we can encapsulate flammable vapors, flammable gases, as well as liquids, thereby separating the fuel from the oxygen on a chemical molecular level. F500, again, it's 100% fluorine-free, non-corrosive, biodegradable encapsulating agent. It is UL listed for Class A and Class B fire suppression. And in the United States, it's actually listed on our Environmental Protection Agency National Contingency Plan as a surface washing agent. So it can be used to treat hydrocarbon spills on the ground. Real quick animation here. We're going to go through what an encapsulator agent is and what happens when it mixes with water, and how that spherical micelle comes to be.
Encapsulator Technology, the next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule, consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic nonpolar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
So that orientation of the agent, both on the surface and the interior portion of the water droplet, is what makes it do everything that it does. And we'll get into specifics here through the next
Encapsulating.
So when we talk about fire suppression mechanics, we know we need to remove one leg of the tetrahedron to suppress a fire. When we're talking about Class B fires, probably the most common old technology is using that mechanical separation of a foam to try and separate the fuel from the oxygen. So we try to put that foam blanket down, separating the fuel from the oxygen, eliminating the vapors that way. Which then can suppress the fire because you're depriving the fuel of oxygen. Issue with that being, if you have a very hot fire, it's going to rapidly break that blanket down. You're going to have to constantly reapply that foam to keep that suppressant blanket in place so you don't have reignition. If it's a three-dimensional fire, so it's something that's a three-dimensional object, or it's a flowing fire where the fuel is actually flowing, that's not conducive to a foam fire suppression because you can't form that foam blanket over that three-dimensional object, or a running fuel fire, a flowing fuel fire. So really has limitations when it comes to that. But when we look at F500 and an encapsulator agent, we have rapid and permanent heat reduction. So kind of the opposite of a foam blanket. Blankets tend to retain heat. You know, we're sealing off both the material so that it can't naturally cool. We're putting a blanket down, which tends to retain heat. So we're rapidly dissipating the heat. We're encapsulating that fuel molecularly inside the micelle. So removing the fuel, separating it from the oxygen. And you'll see some information as we go on from testing that we've had done that we're interrupting vapor phase combustion as well, that free radical chain reaction. So we're attacking the fire tetrahedron on all levels, which gives you superior firefighting capabilities, particularly, in that three-dimensional environment. So we talked earlier about those unique features that the agent being on the surface and the interior portion of the water droplet does for you. The first of those is the rapid cooling. So that F500 skin works like a heat sink and rapidly absorbs that heat to the micelles within the water droplet. So we're getting cooling anywhere from 3 to 10 times more than plain water alone, even more than that when we're talking about a foam. So again, very rapid heat reduction. Second unique feature is that encapsulation that, again, we test through that NFPA 18A77, where we're locking up that fuel, that hydrocarbon, whatever it may be, our combustible inside that spherical micelle. This is the test protocol for encapsulation for that NFPA 18A77 test. So 1 part of F500 to 8 parts fuel to a minimum of 40 parts water, plus the kinetic energy of the water leaving the hose stream. So for our test protocol, the test that we do with every manufactured batch of F500, is we take a gallon of gasoline, we take 16 ounces of F500 and mix in 5 gallons of water. We then test that solution in a minute to ensure that there is no ignition of the fuel. Then it needs to be tested again at 2 hours to again ensure there is no ignition of the fuel. What we're doing is showing that we have a stable spherical micelle in the presence of high heat for an extended period of time. So it shows that the F500 creates micelles, that those micelles are capable of encapsulating a hydrocarbon, and that they don't release that hydrocarbon in the presence of high heat so that it becomes ignitable. Last is that toxin reduction. Pretty interesting study here. I know when I talk to fire departments, to me, because my main concern being in the fire service for my members and other firefighters is the safety of those firefighters. In my opinion, this safety benefit that F500 can give to the fire service is its most important attribute, and that's this reduction of toxins in the smoke. So the testing that was done by Clemson University, they were burning toluene. They did several burns where they sprayed a fine water mist through the smoke column. Then they did a number of burns where they sprayed a 3% solution of F500 through that smoke column. They were drawing smoke samples through the entire experiment. They were shooting a light beam through the smoke so that they could test the opacity of the smoke, see how dark, how light obscuring that smoke was. And then they looked for the soot accumulation inside of that inverted funnel. What those results showed that when the F500 was used, there was a 68% increase in visibility, a 97% reduction in soot, and a 98.6% reduction in soot toxicity. So literally the ability to scrub the IDLH atmosphere and improve those operating conditions for firefighters and the general public as well. If you're caught in that environment, in that smoke-laden environment, it can make it a much less dangerous situation. So from that Clemson study, this information, along with vapor reduction experiments, suggests an interruption of vapor phase combustion, possibly by inhibiting the radical coalescence into soot particles. So what that means in general, so how that happens, is that the F500 molecule was a much denser molecule than plain water. So the free radicals, just like a ball moving through the air, can easily pass through that water molecule because it's not as dense as the F500. With the F500, because the molecule is so much denser than plain water, from 18 grams a mole to greater than 1,000 grams a mole, those free radicals can't pass through that F500 skin and those micelles within the water droplets that's protecting those water molecules. So what you have now is, as opposed to a ball passing through the air that easily travels through the air, it's like trying to throw a ball underwater when we're comparing the density of water to the density of air. That ball can't travel through the same way those free radicals can't pass through that F500 molecule, so it stops them from coming together and forming. So let's now look at some of these Class B fire applications and how F500 can be effective. So the things we're talking about is, gasoline, ethanol, diesel, oils, and for Brazil, in Europe, Asia, the heptane that's used a lot. So this particular fire is E85 gasoline. This was done at a training facility here just outside of Pittsburgh. So we're going to go ahead. There's probably, 5 or 10 gallons of E85 in this pan. Going to be using a single hand line with around 100 gallon per minute nozzle, 3% solution of F500. So one of the things we're going to look at we know if this would be a foam application, we only have 3 ways to apply that foam. We need to bank it on, we need to roll it on, or we need to rain it down. So because this is in a container and there's not a sidewall, the only effective application for foam for this type of fire, which would be a perfect foam application event, would be to try and rain it down on top of that fire. The issue with that is you get a lot of high heat from the fire, breaks the bubbles. It tends to slow the reaction. Here you're going to see we're using a dispersed pattern, sweeping the fire. So we're trying to encapsulate those vapors that are vaporizing and off-gassing. Right now, fire's extinguished. All I'm doing is continuing to cool the steel to pull the heat out of the steel. Because we're not forming a foam blanket to suppress vapors, we're eliminating that reignition hazard by rapidly cooling all of the surrounding structure and all of the surrounding material below the auto ignition temperature of the fuel. You'll see here in a minute, I'll walk up to that tank, even with that extended pre-burn and that very short application of F500, I'll be able to take my hand, the glove off of my hand, and place my bare hand on the side of the steel. So it's literally that cool, that quickly, below the auto ignition temperature of the fuel. We can't get a reignition. We can't get an auto ignition from that fire. Same way here. So we just saw E85. This one is diesel. This is down in Atlanta at the State Fire Academy. Same thing. You would have that limited application. Here you could attempt to form a foam blanket ahead of the fire and roll it on or rain it on. You're going to see the same type of application we used on the E85, a dispersed pattern. We're going to sweep the surface of the fire. We're looking to encapsulate those gases that are off-gassing. So remember, it's not the fuel that's burning. The fuel is heating up and vaporizing. Those vapors are actually what's burning. So we're encapsulating those flammable vapors while we're cooling both the surrounding steel and the material that's burning. Again, removing the heat stops that auto ignition. We don't need to form a blanket because we're eliminating the source of ignition of the fuel. So both of those were great two-dimensional foam application type fires that F500 still handled rather easily. So here's one of those three-dimensional fire events where foam's really not. Okay. So this comes to us from our distributors over in Vietnam. They actually built this tank truck simulator. So they are flowing a combination of diesel and gasoline from the top of the tank. They're going to get a large pool fire below the tank and a running fuel fire down the side of the tank. So large three-dimensional object, not really capable of forming a foam blanket over that entire tank. There actually is a separate video where they attempt to do this with foam, and it takes minutes on top of minutes, and they aren't very successful. At the end, they finally come back to F500 just to finish extinguishing the fire. So they're going to do this with two hand lines, one to the rear of the tank, and then one from the front side here, the camera view. The front side nozzle is going to be a rotating fog nozzle. So think of a cellar nozzle. It's going to do the same type of application, that spinning cellar nozzle, except it's a very fine mist. So the finer the droplet you can get, the more encapsulation and the more cooling we can achieve with F500. So they're using a standard hand line on the rear of the tank and that rotating fog nozzle on the front of the tank. So again, a really good pre-burn. We have the tires involved. That steel is now superheated on the side of the tank. So your ignition source is there to keep that fire continually burning. You'll see here in a second, as soon as they start that front hand line, they charge that line, that very fine fog that's going out. They'll also start now attacking with the combination nozzle from the rear of the tank. So two things to notice here almost instantaneously. Look at the reduced level of smoke coming off the tank. So that's that interruption of vapor phase combustion, stopping those toxins and that heavy black toxic smoke from forming. Secondly, we have the rapid knockdown of the fire. So cooling of the tank while we're suppressing the fire, just like we had with the E85, the fire's now extinguished. All they're continuing to do is to apply agent onto the tank now to cool that tank to stop reignition of a fire. So we're cooling it down, getting all of that steel below the auto ignition temperature of the fuel, continuing to encapsulate the fuel that's still running down the side of the tank so that it can't reignite. So perfect application for an encapsulator agent where foam would not be suitable, that three-dimensional flowing fuel fire. So there are some scenarios, particularly with large above ground storage tanks, where F500 in and of itself isn't the best application, but it can work hand in hand with a foam application. And kind of through an animation here, I'll kind of talk us through what we're seeing and how F500 can work hand in hand with foam, either in a fixed application or through a fire department response to help take a really bad situation and make it better in a hurry. So you kind of have here a standard, what would be a storage facility application, above ground storage tanks that have built-in cooling rings going around them that traditionally would have plain water. These ones would have a 3% solution of F500 for cooling the tank, while they have a foam generator to apply foam to the top surface of the tank. So again, both the F500 spray and your foam manifolds, the bladder tanks or totes, whatever that's proportioning the foam in the F500 through deluge valves, depending on what tank would be on fire. Again, you can have monitors to assist with either application of foam or F500 onto the tank. In the event of a fire, the nozzles around the outside of the tank would spray a solution of F500 to cool the steel, while the foam through the foam chamber is flowed onto the surface of the fire. So we're cooling the steel down, cooling the material down inside, making that foam much more effective, allowing it to seal to the outer rim of the tank. So here, just kind of a simulation. There's a lightning strike that starts the tank on fire. The system activates, so we now have heat detector activated. The system does what it's supposed to do. We're flowing F500 and we're flowing foam. So you have that F500 curtain around the outside of the tank, again, cooling that steel while the foam chamber is applying that foam onto the surface of the fire, working in conjunction. We keep the integrity of the steel. We can also cool the surrounding tanks so that radiant heat doesn't spread the fire from tank to tank. If we have a situation where we need to use master streams, so we had a failure of the system or a boil over, the same type of application, you can come in through those master stream appliances using the F500 to try and cool the tanks, keep as much heat off of the exposed tanks as possible, while we're using the deluge guns to start to apply both foam and encapsulator to cool the steel and suppress the vapors to extinguish the fire. So the ability of both agents to work hand in hand, F500 for cooling, for encapsulation of the vapors, lowering the heat to make that foam that much more effective, laying that blanket down. It takes you remove the heat away from the foam. It makes your foam much more effective and makes it last much longer on that fuel. So it increases your. Now we'll get into some of the spill control applications. And it's not just hydrocarbons. So we're talking about train derailments, accidents, rollovers, just straight chemical spills or chemical leaks, fuel spills, pipeline breaks, all those different applications. So as I said earlier, this is actually our listing from the U.S. Environmental Protection Agency that F500 will be listed on the NCP. That's the National Contingency Plan product schedule under surface washing agents. It may be authorized for use by federal on-scene coordinators in accordance with 40 CFR section 300.910. So that's the approval for F500 to be used as a surface washing agent. So this is a video, a demonstration of that application, that type of surface application we're talking about. So small scale, but you imagine a fuel spill. You know, we had a tanker out in the water that discharged oil, and we now have that oil washing up onto the beach, covering the rocks, covering the sand. Here we're using a 3% solution of F500 in a deck sprayer on these oil-soaked rocks. So the F500 is actually solubilizing that oil, making it a water-soluble solution, runs down into the sand, actually breaks it apart. It makes it much easier for the microbes that are naturally occurring in the soil to go ahead and digest both that hydrocarbon and the F500, rapidly bioremediating both. So again, be it fuel, be it oil, whatever it is, the F500 can rapidly break that down, remove the LELs, make it a non-flammable environment. We've actually been used several times by Colonial Pipeline for various pipeline breaks that they've had in both diesel and gasoline transmission lines, because the LELs were so high they couldn't safely excavate or work in that area where the pipeline break was. So they've used F500 to actually encapsulate that fuel and remove the flammability of that fuel to make it safe to work in that area. But as you can see, even the oil that was stained onto the sand rapidly is broken down and then absorbed into the sand. So here it was applied on a 1/4 inch 3% solution, effective in fresh or salt water. If you do heat the F500, so if you're using hot water, it is much more effective. It breaks that hydrocarbon down much more rapidly at warmer temperatures, at a hotter temperature. So this is another, this was from the Clemson University. So this was a vapor reduction experiment that was conducted at Clemson University, where they were using hexane in a flask, where they introduced F500 into that hexane mixture that checked for the ability of F500 to remove the flammability of that hexane. So here, when they just tested the hexane, they found that the vapors persisted for nearly 10 minutes in the system they were testing. So that's how long the flammability concentrations. When they added the F500, it lowered, concentrations by approximately 38% in 10 seconds and more than 96% within 2.5 minutes. that reduction was maintained during the entire time that hexane was in the flask. So from that Clemson study, these data indicate application of an aqueous F500 to flammable liquids or to their vapors can eliminate that flammability concern which arises from hydrocarbons. Exactly what we find with the applications that Colonial Pipeline has done. It removes that flammability, making it a safe work environment. So again, kind of a fire department scenario, we're going to light this on fire just to demonstrate the ability of F500 to eliminate that flammability. So again, this is E85 gasoline. I'll go ahead and speed it up here a little bit. So we're going to go ahead here. We've got 5 gallons of E85 in the bucket that we're going to spill out on the concrete. So we're simulating a fuel spill. Again, a 3% solution of F500 in this hose stream. So you're going to see the firefighter here is going to treat part of that spill with F500. So streaming the agent into the fuel, encapsulating that fuel and removing its flammability. He'll now take a torch and ignite that fuel that was not treated. As you can see, the only fuel that's burning is the untreated fuel. The fuel uphill that was encapsulated with the F500, again, no bubbles, is non-ignitable. He'll now use the hand line to finish extinguishing the fire. So treating that other fuel, encapsulating that other fuel, again, rendering it non-flammable, non-explosive. And you'll notice not the best technique, but he's actually walking through the solution that he's already encapsulated. Not like a foam where you're going to break the blanket and expose vapors that can reignite. Once the fuel's been encapsulated, it's encapsulated. It can't reignite. In fact, you'll see here in a second, he's going to pick up the torch again that he used to ignite the fuel, and he'll walk through that fuel spill, that encapsulated fuel with the torch, showing that it's non-flammable, non-ignitable. So that's the benefits you can provide with F500, making a scene safe. So with a foam blanket, we get a temporary suppression of the vapors. With F500, you get a permanent encapsulation. No need to reapply the agent. Once you've reached a non-flammable state, it's non-flammable. There's no need to reapply the agent after the fact. Just some reports published on F500. So this was in the Canadian Journal of Emergency Management of an oil spill up in Canada where they used F500 to treat that spill. Again, the highlight out of here is once again F500 proved its worth, and that it was able to suppress both the LELs and also the H2S gas that was coming off of this spill. So again, not just hydrocarbons, but other gases, other VOCs as well. Another one here. So this speaks to not only the encapsulation, but the bioremediation aspects of the agent. So this was a petroleum plant that had a benzene spill. The spill was treated 2 to 3 times a day for 3 days with F500 with a 3% solution. The results were 1 week after the last application, to a depth of 36 inches, there was no trace of benzene left in the soil. In addition to this, they took soil samples away from the spill to have a baseline of what was in the soil. The F500 remediated soil from the benzene spill was cleaner than their test section from elsewhere, that control sample that they took from elsewhere in the facility. So it actually made the soil even cleaner than soil that wasn't involved in the initial benzene spill. some of the other applications here. This is, again, real life scenarios with F500. This was done in Chile. It was a train that had derailed, spilled both diesel fuel from the locomotive and sulfuric acid. Another one here, this was a tanker rollover. So the tanker rolled off the highway down the embankment. This was another sulfuric acid leak where the agent treated that sulfuric acid, neutralized it without having an exothermic reaction. Another one here, again in Chile, they're our go-to folks when it comes to the various asset applications with F500. This was two tractor trailers that ran into each other, ruptured the one tank of sulfuric acid. As you can see here, prior to those guys getting on scene and starting to apply the F500, we did have a vapor release. Here, they've now got the area diked to contain it. They were attempting to bury it. There's still release through the soil. So they're now spraying 3% F500 onto that sulfuric acid to neutralize the sulfuric acid. Again, no exothermic reaction that you would get if you were using plain water. Also, no vapor cloud, again, coming up off of that sulfuric acid release. So this next one, this was out in Globe, Arizona, actually in the US. So this was a gasoline tanker that rolled over the side of a hill. Again, didn't really have a safe way to get the gas tanker back up onto the interstate, back up onto the highway. So they decided, they sent some crews down to open the scuttle hatches on the top of the tank, attach some cables. They were going to roll the tank over to drain the gasoline out. So prior to this, they set up some remote monitoring so they could monitor the LELs in the air. And now they're applying a 3% solution of F500 while they roll the tank. As you can see, the fuel draining out of the tank so that they can empty the tank to be able to lift the truck back up to the highway. So in doing this, they kept it a safe working environment, kept the LELs down so they didn't have a flammable, explosive environment as they drained the tank. They then continued to use F500 after, as they raised it back up to the road. So again, multiple tow trucks or cranes here lifting that truck and tank back up onto the highway while they're still flowing a F500 solution onto the ground and the tank, suppressing vapors to keep the vapors down so that they didn't have an explosion from a spark while they were trying to move the truck. So when we talk about the benefits of encapsulator technology, yes, we can use it for fire suppression. We can also use it for vapor mitigation. We can use it for spill control of both hydrocarbons and other VOCs, chemicals, acids, and it gives you the ability to actually bioremediate that spill so you can save some time over excavating that soil and removing the soil. It'll actually speed up that naturally occurring bioremediation process. Thing, Hernan, thanks for giving us your time. Something out of tonight's presentation, tonight's webinar. Like Hernan said, with any new technology, education is the key. And I thank you for wanting to be educated. So again, questions, feel free to reach out. info@hct-world.com. That's probably the easiest way if you don't have a specific person's email address to get your questions answered. But again, enjoyed the conversation we had this evening, and look forward to hopefully meeting everybody in person here sometime in the future.